Just to review, in previous chapters we introduced methods of inferential statistics. We've always dealt with samples from a single population. Now, we want to extend the methods we have for testing hypotheses to situations involving two sets of sample data. For example, if we test the claim that when college students are weighed at the beginning and the end of their freshman year, the differences show a mean weight gain of 15 pounds. Another example would be testing the claim that the proportion of children who contract polio is less for children given the Salk vaccine than for children given a placebo. And third, we could test the claim that subjects treated with Lipitor have a mean cholesterol level that is lower than the mean cholesterol level for subjects given a placebo. In each of these examples, we have situations involving two sets of sample data. When we use sample data from two independent samples to test hypotheses made about two population means, or if we want to construct a confidence interval estimate of the difference between two population means, we have to first understand the difference between an independent versus the dependent sample. An independent sample would involve two samples where the sample values from one population are not related to or somehow naturally paired or matched with the sample values from the other populations. Dependent samples involve situations where the sample values are paired in some way. Each pair of sample values consists of two measurements from the same subject, like a before or after, or each pair of sample values consists of matched pairs, such as husband and wife data, where the matching is based on some inherent relationship. Let's look at independent versus dependent samples. Here's an independent sample. The University of Arizona psychologists conducted a study in which 210 women and 186 men wore microphones so that the numbers of words that they spoke could be recorded. The sample word counts for men and the sample word counts for women are two independent samples because the subjects were not matched or paired in any way. Now let's look at a dependent sample. Rutgers University researchers conducted a study of 67 students who were weighed in September of their freshman year and again in April of their freshman year. The two samples are dependent because each September weight is paired with the April weight for each student. Now we want to discuss the notation for testing a claim about two independent population means. Since we have two different populations, we're going to have two separate means and two separate standard deviations, etc. So for population 1, we let mu sub 1 be the population mean, sigma sub 1 is population standard deviation, n sub 1 is size of the first sample, x bar sub 1 is the sample mean, and s sub 1 is the sample standard deviation. The corresponding notations with subscript 2 will be used for the second population. Next, let's discuss the requirements for testing a claim about two independent population means. First, the population standard deviation for both samples must be unknown, and we are not going to assume that they are equal. The two samples must be independent. Both samples must be simple random samples. And then either or both of these conditions below must be satisfied. Either the two sample sizes are both large, with both of them being greater than 30, or both samples must come from populations that have normal distributions. Now, typically we've been using p-values for our hypothesis tests. The p-value method of hypothesis testing, the traditional method, and confidence intervals all use the same distribution and standard error, so they are equivalent in the sense that they result in the same conclusions. In order to look up p-values for this type of hypothesis test, you need a statistical program or graphing calculator to do so. So we're going to assume that we're not working with technology like that, and we'll be using the traditional method of hypothesis testing. Now let's look at the test statistic formula for a hypothesis test involving two means with independent samples. First, we often assume that the difference between both population means is 0. This means we're making an assumption that the population means are the same. Here's our test statistic formula. So it says that t is equal to x bar 1 minus x bar 2. So we want to subtract the sample means. And then we subtract the next value, which comes from subtracting the population means. And for most of our problems, this is going to be 0 because we're assuming that there is no difference between the population means. We divide that by the square root of standard deviation 1 squared over n sub 1 plus standard deviation squared over n sub 2. So this part of the formula says you need to square each sample standard deviation and divide that by its sample size, and then you add those values and square root the answer. Let's look at a study that was done to determine if men and women are equal talkers. A headline in USA Today proclaimed that men/women are equal talkers. That headline referred to a study of the numbers of words that samples of men and women spoke in a day. Given below are the results of the study. Use a 0.05 significance level to test the claim that men and women speak the same mean number of words in a day. Does there appear to be a difference? So in this table we have the two different groups, men and women, and we have n sub 1 is 186, so there was 186 men in the study. N sub 2 is 210, so there were 210 women in the study. And then the sample mean for men is 15,668.5. The sample mean for women was 16,215.0. The standard deviation of the sample of men is 8,632.5, and the standard deviation of the sample for women is 7,301.2. We need to always do a requirements check. So first, we check that the values of the two population standard deviations are not known, and we're not making an assumption that they are equal. Also, these two samples are independent because the word counts for the sample of men are not matched or paired with the word counts for the sample of women. Third, we can assume that the samples are simple random samples. 4. Both samples are large, so it is not necessary to verify that each sample appears to come from a population of normal distribution. So the requirements are satisfied for the hypothesis test. So now let's proceed with setting up the claim and hypotheses for this example. So the first step is to set up the claim, and since we're testing a claim that the men and women speak the same mean number of words in a day, we have mu sub 1 minus mu sub 2 is equal to 0. The null hypothesis is always equal, so this is going to say that mu sub 1 minus mu sub 2 equals 0 like our claim does. And then our alternate hypothesis states that mu sub 1 minus mu sub 2 is not equal to 0. So the alternate must either match the claim or be the opposite of equal. Since our null hypothesis states that mu sub 1 is equivalent to mu sub 2, we're assuming they're equal, then in the test statistic formula we assume that the value of mu sub 1 minus mu sub 2 is 0. Here's our test statistic formula. So we plug in our values and we get our x bar 1 minus x bar 2, and we subtract 0 from that value since we're assuming that the population means are equal. We divide that by each standard deviation squared divided by its sample size, and then this gives us negative 0.676. Since this is a t distribution, we want to round to 3 decimal places. The third step in a hypothesis test is to find the critical values. So we first need to look up the degrees of freedom, and for two samples, since you have two different sample sizes, you always want to go with the smaller sample size or the smaller n minus 1 value. So I'm going to use the 186 minus 1 equals 185. The area in two tails is going to be 0.05. That comes from the significance level of the test. Table A3 does not include 185 degrees of freedom. So we decide whether to use the 100th row or the 200th row. And since 185 is closer to 200, we can use the critical values that line up under the 0.05 area in two tails in row 200. That leads us to the result that the critical values are plus or minus 1.972. Remember that instead of finding the p-value, we're going to draw a picture to determine if our test statistic falls within the critical region bounded by the two critical values. This is using the traditional method of hypothesis testing. To set up the traditional hypothesis test, we first graph a standard normal distribution curve, and the center of it, that's normally our mean. What we want to put here is our null hypothesis, which states that mu sub 1 minus mu sub 2 is equal to 0. Next, we want to make a mark at each of our critical values on the curve. So I had a mark at negative 1.972 and positive 1.972. The area that falls between these two critical values means that if my test statistic falls there, it's outside of the critical region, and so I would fail to reject the null. The area that's located in each tail beyond the critical value is called the critical region, and if my test statistic happens to fall in either of those red areas, then I would make the conclusion to reject the null. So now all we have to do is figure out where our test statistic value falls. So the test statistic we got was negative 0.676. That value does not fall within the critical red regions, and so I would make the conclusion to fail to reject the null hypothesis. Now let's go ahead and form the conclusion and make our statement. So we said to fail to reject the null since the test statistic didn't fall within the critical region. That leads us to say that there is not sufficient evidence to warrant rejection of the claim that men and women speak the same number of mean words in a day. So there does not appear to be a significant difference between the two means. Next, let's look at a formula that helps us set up a confidence interval estimate for two means from independent samples. So the confidence interval estimate of the difference of the population means mu sub 1 minus mu sub 2 is x bar 1 minus x bar 2 minus e is going to be less than the difference between the population means, and that's less than x bar 1 minus x bar 2 plus e. E is the margin of error, so let's take a look at that formula. So E is t sub a over 2 times the square root of sample mean 1 squared over n 1 plus sample mean 2 squared over n sub 2. We have to look up the critical value t sub a over 2 in table A3, and that's the same critical value that we get when we do our standard hypothesis test. And then inside we square each sample standard deviation and divide by the sample size, and then add those values and square root the answer. Using the sample data below, construct a 95% confidence interval estimate of the difference between the mean number of words spoken by men and the mean number of words spoken by women. So this is the same sample data that we used for example 1. The difference is we want to set up a confidence interval for this example. So the requirements check is the same. Check to make sure that the values of the two population standard deviations are unknown, and we're assuming that they're not equal. And the two samples are independent, and we assume that the samples are simple random. And both samples are large, so you have to make sure that they're either greater than 30 with the size or that they're normally distributed. So the requirements for this are satisfied. Next, we find the critical value. So we have to determine the degrees of freedom, and we still go with a smaller sample size. So we take 186 minus 1 equals 185. And we want a 95% confidence interval, so you always subtract that percentage from 100% to find the area in the two tails. So 100% minus 95% is 5% in two tails. So when we look in our table A3, we're going to line it up under an area of 0.05 in two tails. Remember, the table A3 didn't include 185 degrees of freedom, so we ended up using the 200th row. When we do that and we line it up with the area of 0.05, we use the critical values at plus or minus 1.972. That's going to be our t sub a over 2 number for the confidence interval formula. Second, we need to find the margin of error E. So here's our formula, and when we substitute in, we just found the critical value t sub a over 2, and that's going to be 1.972. We multiply that by the square root of each standard deviation squared over its sample size. We add those values up. When you figure that value up, you get 1595.4. That's going to be the entire margin of error number. Now we set up the confidence interval estimate. And so this is following along the procedures with this, but we want to first determine what is x bar 1 minus x bar 2. So that's just saying subtract your sample means. So when I take the first sample mean and subtract the second from it, I get negative 546.5. So then my confidence interval estimate will be that value, negative 546.5, plus or minus the margin of error. And I found the margin of error was 1595.4. So first we would take negative 546.5 and subtract 1595.4 to get the lower number, negative 2141.9. And then I would take negative 546.5 and add 1595.4 to get the upper number in the range of 1048.9. So our interpretation of this means that we're 95% confident that the limits of negative 2141.9 words and 1048.9 words actually do contain the difference between the two population means. And because if you go from that negative number to that positive number, you are going to go over the number 0, then since those limits do contain 0, that means that it's very possible that the two population means are equal. So there's not a significant difference between the two means. So whenever your n numbers, one's negative and one's positive, you can make the same conclusion, and you would say that because the limits contain 0, then it suggests that it's possible that the two means could be the same. For our third example, we're going to look at a study involving the heights of supermodels. The heights are measured for the simple random sample of supermodels Crawford, Bunchen, Pestova, Christensen, Hume, Moss, Campbell, Schiffer, and Taylor. They have a mean of 70.0 inches and a standard deviation of 1.5 inches. A data set lists the heights of 40 women who are not supermodels, and they have heights with a mean of 63.2 inches and a standard deviation of 2.7 inch. Use a 0.01 significance level to test the claim that the mean height of supermodels is greater than the mean height of women who are not supermodels. So I set up a table that arranges my supermodels first and then my sample of women second with their sample size n, their sample means, x bars, and then both of the standard deviations. Next we do a requirement check for the hypothesis test. First, the values of the two population standard deviations are not known, and we are not making an assumption that they are equal. Second, the two samples are independent because the heights for the sample of supermodels are in no way matched or paired with the heights for the sample of women. Third, we are told that the samples are simple random samples. And fourth, while the first sample is small and the second is large, we are told that the samples are normally distributed. So the requirements for the hypothesis test are satisfied. The first step is to set up the claim and hypotheses for the test. Since we're testing a claim that the mean height of supermodels is greater than the mean height of the women in the sample, we would set up our claim to state that mu sub 1 minus mu sub 2 is greater than 0. Our null hypothesis is always equal, so this statement would be mu sub 1 minus mu sub 2 equals 0. And then our alternate hypothesis in this case will match the claim. Also, since our null hypothesis states that mu sub 1 equals mu sub 2, we assume that their difference is 0 in the test statistic formula. Next, let's set up the test statistic formula for this one. So we have 70 minus 63.2 is the subtraction of the two sample means, and then we subtract 0 from that. And then we divide that by the square root of each standard deviation squared divided by its sample size. And we add those values together. So the numerator I get 6.8, my denominator 0.6565, and that gives me 10.343 for the test statistic. Third, we want to look up the critical values. So we find the degrees of freedom, and for two samples we go with a smaller population size. So n minus 1 would give us 8 for the degrees of freedom. Since we have a 0.01 significance level, that would be the area contained in two tails. And when we look that up in table A3, we go to the 8th row and we go under 0.01 area in two tails, and we find critical values are at plus or minus 2.896. Now, since this is a right-tailed test involving greater than, we're only going to use the positive critical value when we do our graph. And then instead of finding a p-value, we will draw a picture to determine if our test statistic falls within the critical region bounded by the critical values. This is using the traditional method of hypothesis testing. Next, we set up our picture of the standard normal distribution curve, and I make a mark at the positive critical value of 2.896. The middle is always going to be matching up with the null hypothesis in our hypothesis test. If our test statistic is not going to be contained in the area beyond the critical value, so if it falls in the region to the left of our critical value, then we would fail to reject the null. However, if our test statistic falls within the critical region, which is beyond the critical value, then we would reject the null. So now we graph our test statistic. It's positive 10.343. This is located in that red critical value region. So then our conclusion would be, since it does fall within that region, we want to reject the null hypothesis. So our conclusion was to reject the null hypothesis since the test statistic does fall within the critical region. There is sufficient evidence to conclude that mu sub 1 minus mu sub 2 is greater than 0. So there is sufficient evidence to support the claim that the mean height of supermodels is greater than the mean height of women who are not supermodels. Now let's look at a situation where we take those heights of supermodels and we construct a confidence interval estimate. So we're going to construct a 98% confidence interval estimate of the difference between the mean height of supermodels and the mean height of women who are not supermodels. And then we want to interpret the result. So we're using the same data that we used for example 3. Next, we do a requirements check, and this is the same requirements check that we did for example 3. So our ultimate conclusion was that the requirements are satisfied. So now let's look at the critical value for this hypothesis test, and the degrees of freedom from the smaller sample size was 9 minus 1 equals 8, and we want a 98% confidence interval estimate. So we always subtract that percentage from 100% to find the area contained in two tails. This gives us 2%. So when I go to table A3, I'm going to go to the 8th row, and then I'm going to line up under 0.02 area in two tails. This gives me the critical values are at plus or minus 2.898. Next, we find the margin of error E. So here's our formula, and then our t sub a over 2 was the critical value 2.896, and we multiply that by the square root of standard deviation 1 squared over sample size 1 plus standard deviation squared from the second sample divided by the second sample size. And this gives us 1.904 for the margin of error. The third step is to set up the confidence interval estimate using that margin of error that we just found. So we first have to figure out what value we get when we subtract the two sample means. So we take the first sample mean and subtract the second sample mean from it, and for this we get 6.8. So to figure out the confidence interval, we want to take 6.8 and add and subtract the margin of error. So we add and subtract 1.904. To find the lower number, we take 6.8 minus 1.904, that gives us 4.9, and then the upper number is going to be 6.8 plus 1.904, which is 8.7. So we have that the interval ranges from 4.9 inches to 8.7 inches, and that's the difference of the two population means. So we can conclude that we're 98% confident that the limits of 4.9 inches and 8.7 inches actually do contain the difference between the two population means. Now, in this situation, both of the numbers are positive, so these limits do not contain the value 0. This confidence interval suggests that it is possible that the two means are not equal. So the mean height of supermodels is greater than the mean height of women who are not supermodels. For our fifth example, we're going to look at a statistical test involving longevity. Listed below are the numbers of years that popes and British monarchs since 1690 lived after their election or coronation. Treat the values as simple random samples from a larger population. Use a 0.01 significance level to test the claim that the mean longevity for popes is less than the mean for British monarchs after their coronation. So this time, instead of giving us the sample size with the sample mean and the sample standard deviation for both groups, they give us the set of data. And so what we have to do is enter this data separately into the calculator. So you're going to set up your calculator using one var stats, and you're going to type in all your numbers for the popes, and then you want to record your X bar number, your S standard deviation number, and your N, your sample size. Then you clear your data and then do the same thing for the British monarchs. So from the calculator we get this data, which I set up in a table, and I have the popes, and I had my sample size was 24, the mean was 13.125, and the standard deviation 8.96. And then for the British monarchs, that sample size contained 14, and its mean was 22.714, and its standard deviation was 18.60. Now let's do a requirement check for the hypothesis test. First, the values of the two population standard deviations are unknown, and we're not making an assumption that they're equal. The two samples are independent because the longevity for popes are in no way matched or paired with the longevity for British monarchs. And we're told that the samples are simple random samples, and we want to treat the values as simple random samples from larger populations. So it's not necessary to verify that each sample appears to come from a population of normal distribution. So for us, the requirements are satisfied, and we can proceed with the hypothesis test. Next, let's set up the claims and the hypotheses. So since this situation involves testing a claim that the longevity of popes is less than British monarchs, we want to use the less than symbol in our claim. So we have the population mean 1 minus population mean 2 is less than 0. The null hypothesis is always equal. So here we have the difference between the population means is equal to 0. And then our alternate hypothesis will either be matching the claim or be the opposite of equal. And so in this situation, we need to match the claim. Then we find the test statistic. So I have 13.125 minus 22.714 minus 0 divided by the square root of 8.96 squared over 24 plus 18.60 squared over 14, and this equals a test statistic of negative 1.810. Next, we're going to find the critical values for this test. We always use the degrees of freedom for the smaller of the two samples, so we have 14 minus 1 equals 13. Also, we were told to use a 0.01 significance level for our test. So when we go to the 13th row of table A3, we want to line up under the column that has 0.01 for the area and two tails. This will give you critical values of plus or minus 2.650. Since this involves a claim of less than, we only want to use the negative critical value, which will shade the tail to the left of that number. Next, instead of finding a p-value, we will draw a picture to determine if our test statistic falls within the critical region that is beyond that critical value. This picture will mean, does it shade to the left, and does our value fall within that region or not? So to set up our graph, we sketch the standard normal distribution curve, and we have in the middle our null hypothesis statement. Then we make a mark at our critical value, which was negative 2.650, and we shade that region to the right. That is our critical region. If our test statistic falls within that area, we would make the conclusion to reject the null. Second, we shade the area to the right of that critical value, and that whole region, if our test statistic falls there, we would fail to reject the null. So let's graph our test statistic. It is negative 1.810. Because the test statistic does not fall within the critical region, we fail to reject the null hypothesis. Our conclusion was to fail to reject the null since the test statistic did not fall within the critical region. So to interpret that, we would say there is not sufficient evidence to conclude that the difference between the population means is less than 0. So there is not sufficient evidence to support the claim that the mean longevity after election for popes is less than the mean longevity after coronation for British monarchs. Now let's practice setting up a confidence interval estimate. We want to do a 98% confidence interval estimate of the difference between the mean longevity for popes and the mean longevity for British monarchs. And then we want to interpret the results. So here's my data that I got from example 5, and we're going to jump into finding the critical value next. So to find the critical value, we first use the degrees of freedom for the smaller of the two samples. So we have 14 minus 1 equals 13. We want a 98% confidence interval, so we subtract that from 100% to find the area in two tails. This gives us 2%, which is 0.02. So we want to go to the 13th row and go under the mark at 0.02, and we find that the critical values are plus or minus 2.650. This value would be the t sub a over 2 number for the confidence interval estimate formula. Now we find the margin of error E. So using our formula, we have that the critical value t sub a over 2 is 2.650. We multiply that by the square root of 8.96 squared over 24 plus 18.60 squared over 14. That product gives us 14.038. That is the margin of error E. Third, we're going to set up the confidence interval estimate. So here's our guideline, and then we want to first subtract the sample means. And so x bar 1 minus x bar 2 is 13.125 minus 22.714. This gives us a difference of negative 9.589 for the sample means. The confidence interval comes from taking that number and adding and subtracting the margin of error. So I have negative 9.589 plus or minus 14.038. This gives me a range of values from negative 23.6 to 4.4 years. So we are 98% confident that the limits of negative 23.6 years and 4.4 years actually do contain the difference between the two population means. Because this ranges from a negative to a positive, then we know that the limits do contain 0. So this confidence interval suggests that it's very possible that the two population means are equal, so there is not a significant difference between the two means.